All right, let's go ahead and get started. I just did this about an hour ago, but I extended the 4.5 web work to Friday night. Just in case everybody wants to come to office hours to talk about that. You'll be able to do that tomorrow or Friday. Again, look at that stuff as soon as possible. I know it's a pretty hard section. Any more questions before we go? All right, so in sticking with antiderivatives, so remember, we've spent the vast majority of the semester looking at derivatives and taking them. Now we're doing this inverse process. So I want to find an antiderivative of this G prime here. So let me remind you of something. If you're taking a derivative of a function that has a bunch of terms added together, how do we usually handle that? Right, so you can just do sums and differences term-wise. You just take one term at a time. So thinking about it that way, what's a function whose derivative is 4 cosine x? Okay, are we sure? What's the derivative of 4 sine x? Okay, we're good. I mean, at this point, you're obviously going to be a lot more comfortable with derivatives, so checking yourself is something that's a good idea to do. How about that other thing, 20x to the fourth minus the square root of x cubed all over x? Is that something we can handle? Any suggestions about that one? Yeah. What are you trying to reverse right now?
Well, for quotient rule, it would be squaring bottom, so it would be squaring x. Is that how you do that? Or
So
you have to completely.
the reversing the quotient rule in that way is going to be a much more involved thing. So product rule, quotient rule, those are not things we're going to have right now. But what we can do is this, because I have no idea what function has a derivative that looks like that, but what I can do is simplify this. So first I'll write this as 20x to the fourth over x minus the square root of x cubed over x. Are we okay with that? Can I keep simplifying from there? What does that middle term become? 20x to the third. How about the final term? What's the power on x in the numerator? In the numerator? There should be 3 halves, right? Yeah. So 3 halves minus 1 is going to be minus x to the 1 half. So from there, is that an antiderivative we can handle? I mean, we already did the first term, so this will be 4 sine x. We're going to handle the rest of those one at a time. So how do I find a function whose derivative is 20x cubed? Or how do I find the antiderivative of 20x cubed? What kind of approach would you like to use? Add 1 to 3. So let's just do this real systematically. So 20 times x to the 3 plus 1. Is that all of it?
Yeah, divided by that.
Divided by 3 plus 1, right? So think about the way that the power rule for derivatives works. First, you metaphorically speaking, bring down that exponent and multiply by whatever the overall term is, and then you decrease the exponent by 1. In this case, and I know we said this a couple times last time, but the reminder is always valuable. Now you're doing the opposite. So basically you're doing the opposite of those 2 steps and in the reverse order. So raising the exponent by 1, then dividing by whatever that exponent is.
So it's 5x to the 4th.
Yes. Can we do the same thing to x to the 1/2? Okay. So what's that antiderivative going to become? What was that, Jared?
Well, it's gonna be plus 1 to the exponent, so it's 3/2 and then divided by 3/2.
Okay, so for now, let's leave it like that. We'll clean it up a little bit, but are we okay with what we have here? Okay, so now we can clean things up. So this antiderivative is 4 sine x plus 5x to the 4th. This looks like I'm adding 1 to the whole thing. Minus 2/3 x to the 3/2. All right, how do you feel about that antiderivative? Is it perfect? Or is it missing something?
Let's see.
Yeah. So again, when we take an antiderivative, what happens to constants when you take a derivative? Okay, yeah, it goes to 0, right? So when you're going the opposite way, constants might appear. I mean, how many antiderivatives does this function have here? The one I started with. An infinite number, and they're all kind of represented by this constant. So if I gave you another antiderivative, it would have to be the same as this, but it could differ by the constant. Otherwise, it has to be exactly the same.
And then this equals the capital G of x. That's what we call it.
So in this case, it's lowercase g. Why?
Because that's what it says.
But why? Like kind of what? This is just a convention. This is kind of a tradition, for lack of a better word. I called the thing I was taking the antiderivative of g prime, right?
Mm-hmm.
So
not capital.
g prime is the derivative of what typically?
Yeah.
Lowercase g. So I think, yeah, the last time I said that, a capital letter signifies that it's the antiderivative of something else. We also have this other kind of notation in place for its primes. Any questions there, or any more questions? Okay, how about this? So now I have f prime that I'm giving you. I want to find f. What do you want to do first? Can we find out what f is? What's the antiderivative of e to the x?
E to the x.
Okay. Yeah, so that function has its, it is its own derivative, so it better be its own antiderivative. How about the other thing, the 20 times 1 plus x squared to the negative 1? Do we have an antiderivative for that? Or do we know functions whose derivatives look like that? Yes, you do, but it might not, it might be a little hidden right here. So it's inverse tangent, right? Is it more obvious now that it's written like that? That's typically the way that it's presented, right? So, and I think if we think back a couple months ago, if you want to watch the recordings, but you probably also remember, there are lots of times where I asked you for a derivative and you can't really jump into that. It really does you some good to rewrite and see if anything jumps out at you. So the antiderivative of 20 over 1 plus x squared is what? 20 inverse tangent of x. All right. Is that a good antiderivative?
We'll also need the plus C.
Yeah. But here's the thing. I have enough information to get from that the infinite number of antiderivatives this could be and boil it down to one. Because I have, right, so basically, if you think about this in terms of a graph, which might be the easiest way to see it, if you graph the antiderivative, really I can just slide it up and down, right? Because I don't know what that constant is. But now in this case, since I have a single point on the curve, I know where they all are. So how can I find this value of C based on using that information? So f of x equal to what? -2, and that's equal to e to the 0 plus 20 times the inverse tangent of 0 plus c. What is e to the 0? Just 1? What's the inverse tangent of 0?
Is that also 1?
No, 0. The tangent of 0 is 0. So this means that c is equal to what?
-1.
Should be -3, right? So this right here is our general antiderivative, which you can always find. This new information we got means that we found something else, which is related, but it has one very important difference. This is the particular antiderivative, which you can't always get these. What information do I have to give you?
One value.
I have to give you, well, one pair of values. So I have to give you an x and a corresponding y to make that happen. How good? Any questions? All right, how about this one? From here, I want to find f given this information. So what do we do? What does that stand for? You notice something?
Well, yeah, we're gonna have to reverse it twice,
How come?
because that's the double derivative.
Right, so
Second derivative.
that's the second derivative, right? And I'm trying to get back to whatever the parent function f is. So what do I have to do first? Can I find f right now?
No, first you gotta find f prime.
Right, so I have to do that first. So f prime is equal to what? 4x cubed plus 3x squared. What happens to the -4? Minus 4x. Good. Now good. Isabel? Yeah. And I'm pretty sure that was said, but I didn't write it that way. 4x cubed. All right, now is it good? Can I find C?
No,
Why can't I find C?
because the values I was thinking is different.
Yeah, I don't know anything about, I don't have any points on the derivative. Go ahead.
So because that's true, we don't have to worry about C until we get to the parent function? Like,
Not
it's-
only do you not have to
it's
worry
not
about it, you
gonna
can't
matter.
do anything about it right now. Yeah, you don't have enough information to figure that out. Isabel?
Does that mean that when we end, we're gonna have two pairs of C's? Like C plus C?
Let's figure that out right now. Okay, so now can we figure out what f is, or at least something about f? Okay, so now we'll go to f of x. And what does that one look like? X to the fourth plus x to the third minus 2x squared. What happens to the c? What is C? What kind of a thing is it? It's a constant, right? And what's the antiderivative of a constant? Cx, right? And compare that with what you did to -4. Took an antiderivative of -4, which is a constant. So that antiderivative is -4. I don't know what C is, but I know it's a constant, so I can treat that. Is that antiderivative good?
No.
There's something else that's missing. Remember when you take any antiderivative, there's another constant. I don't want to call it C though. Because if I call it C, what am I kind of assuming? That it's the same as the other constant, right? And there's absolutely can't assume that. So I'll just call it something else. So I have two handles to deal with. So this right here is the very, very general antiderivative or the very general form of F. So I have enough information to figure out what C and D are.
Yes.
Cool. So what do I do? How do I make use of that information?
Choose values that equals that and then plug in the X value for that.
Okay, so if we use f of 0 equals 4, what's gonna happen here?
Plug in 0, all the X's set equals 4.
So then 4 is equal to what? D. So yeah, setting x to 0, and I'll say this, because x is equal to 0 when y is equal to 4. Setting all the x's equal to 0 makes all the other terms except for d vanish. All right, so I got d equals 4. Now what? Find c. So if I plug in 1 for f of x, I get 1 equals 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus c times 1 plus 4. So 1 equals 1, 2, just 1 equals c plus 4. So c is equal to -3, which means I can give my final antiderivative like this. X to the 4th plus x cubed minus 2x squared minus 3x plus 4. Any questions with that? Okay. So, yeah, go for it.
So why can we assume that f of 0 equals 4 for the first thing we're plugging in? Just
Because I gave that to you.
Okay.
Yeah, so
I guess that does make sense.
so yeah, here are all the things I know about f to start with. Its second derivative is this, and f has these 2 points. So yeah, without all that information, I have no way of getting f beyond what those constants are, or beyond those, just leaving those constants arbitrary. Okay. All right. So looking back, how are the physical quantities of position, velocity, and acceleration related to one another? So we've done these in the past. We've dealt with all three. So let's just pick any two of them. Position and velocity. How is position related to velocity?
Velocity is the rate of change of position.
Velocity. So velocity is the, I'll say, instantaneous rate of change of what? Position. Which is true by definition. How have we used that fact in the past to, mathematically unite velocity and position?
Well, like what functions, like if position was your original, velocity would be grad prime, and then
Right.
acceleration would be the delta prime.
Yeah.
So another way we can say this is, velocity is derivative of position with respect to what variable though? Time, right? So a couple ways to confirm that or to convince you of that. Velocity is measured usually in what?
Some percent.
Something per, yes, some length per some time. So velocity by definition is the rate of change of position or rate of change of displacement over time. All right, how about acceleration? How's acceleration related in the asset?
So
Isabel,
Acceleration is the rate of change from velocity.
okay, so can I just borrow the same sentence?
Yeah. And units of time, which is why it's squared.
So we've been talking about antiderivatives the last couple of days. Can we reverse our thinking with these three terms in the language of antiderivatives?
velocity is the time, acceleration, position is the same as the velocity.
Right. So we can, just as we use differentiation to travel from position to velocity acceleration, we can use anti-differentiation to travel the other direction.
So can you call position the second anti? Of
That is
acceleration?
not a term I've heard, but it's the antiderivative of the antiderivative. But yeah, I taking the second derivative and something double prime, those are like well-traveled. That's well-traveled math language. I've never heard of the second antiderivative or the second. I almost used a word I don't want to use right now, but we'll get to it soon. So let's use this thing now. So I have a particle that's moving in a straight line. I know its acceleration. I want to find the position function. So I'm given acceleration. I eventually want to get to position. What can I do now? What should I do right now? So I have acceleration and I want to get to position, right? Can I do that directly?
No.
What can I do directly, like right now?
Acceleration, well, you can get the velocity.
I can get the velocity, right? So how do I get to velocity when all I have is acceleration? Take the antiderivative of AT. So A of t is equal to 6t minus 4. What can that tell me about velocity with respect to time?
It's 3t squared minus 4x plus c, and you said it equals -6, and then plug in 0 for t.
Okay, so let's stop at the velocity. Are we okay with why that velocity function, where it came from? So all comes from the fact that really, as we said 2 months ago, an acceleration is the rate of change of velocity over time. Now we're undoing that reasoning to find velocity as the antiderivative of acceleration. So Solomon, you said a couple things. You said you wanted to basically say v of 0, which is equal to 3 times 0 squared minus 4 times 0 plus c. This is equal to what?
-6.
All right. I think I see where the -6 comes from. Where did the 0 come from?
Initial velocity.
Okay. And this is a kind of a loaded word. Initial implies what?
Beginning.
Yeah, beginning. So time equals 0. So right when I start measuring something. So I agree with this. This logic. So what is c equal to then?
-6.
C is equal to -6. So now I have the velocity in particular is 3t squared minus 4t minus 6. Okay, what can I do with that?
I'll get that.
Take the anti position.
Okay, so from here I can get the position. What's that equal to?
t cubed minus 2t squared minus 6x plus t.
Do I have enough information to get C this time?
Yes.
So I know that S of 0 is equal to what?
9.
9, which means that C is equal to 9. So here's my final particular position function. Just to kind of bring it all back to earlier in the semester. I mean, long ago, I could have given you this position function. You could have found the velocity and acceleration. Now we're just going the opposite direction. Not just, I mean, it's not a simple thing, but it is related to things that you've gotten comfortable with. Any more questions here? Okay. All right, so let's do one where we gotta kind of figure out what the formula is. So I have a ball thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. I want to find its height above the ground 2 seconds later. So is there anything I know right now?
No velocity.
I know velocity for all time or just a certain time?
Yeah, I guess at a certain time.
I don't think I've made it clear here. I'm throwing it straight. Oh yeah, I'm throwing it straight up.
Yeah.
If you could throw something straight up at a constant speed, then you can't do that, right? I'm just highlighting the fact that 48 feet per second is that's not the speed all the time.
No.
So what's the thing that's gonna cause that speed to change?
Gravity.
Gravity, right? So what do we know right now? So I'm trying to find position, or specifically vertical position, height. I know something about the velocity, but I don't know a lot about the velocity. Do I know anything about the acceleration? What do I know about the acceleration?
-9 point.
If we were dealing with meters, I would agree.
Oh, yeah.
So
And I
anyone know what that number is in
don't know, it's feet.
freedom units? So this acceleration is -32 feet per second squared. Is that constant?
Yes.
Yeah. So yeah, we can assume very, very roughly, or I mean, acceleration is constant for our purposes. That's gravity in English units, yeah.
Okay. So we would just have to leave that.
And I mean, most of you are taking physics classes or have taken physics. Have you ever seen that before?
Actually, no.
So I mean,
I've only seen the meters version.
exactly. I've never taken a physics class where we dealt with this, right? So yeah, it's not a big deal that you don't know that number. But 9.8, yeah, that's one you'll commit to memory whether or not you want to. So this is our constant acceleration. What can we do with that? Antiderivative, which will give us what? Not what number, but like what idea?
It'll give us velocity,
Give us the velocity, right?
and then we can plug in the 48.
So what is this velocity? That it?
Oh,
Let's see. Do I know what that C is?
yes. Okay.
Why do I know the C is 48? How do you know that when V is 48, T is 0? Or do you know that?
Yeah, when T is 0.
Yeah, so I'm trying to find the height over the ground. T seconds later, maybe it's not totally clear, but that's after I throw the ball, right? So that 48 feet per second, yeah, I didn't use the word, but it really is the initial velocity. So now I have velocity. Now what can we do? Or what do I want? I should ask, make sure we understand that.
Back to the position of the single way.
Okay, and this time I'll call it H of T. What would that antiderivative be? Why did I put a square here? Oh, you guys let me get away with a lot of nonsense. Maybe this new antiderivative will make it clear why I did that. What's the antiderivative? So let me first back up. Are we okay with why this is what should be going on?
Yes, yes.
Okay, I tried to jump a level. So what is the position function from here?
Now that's, yeah, now it's the negative 16 G squared.
Right. So let's keep going.
Yeah. 48T plus
Plus C. So I know enough information to give you what C is.
This is plus the 4.
Yeah, so yeah, the cliff is above the ground. So I'm starting off with some, let's make this clear. I can say that V of 0 is equal to 48, right? And I can also say that H of 0 is equal to 432. So H of T for all T will be negative 16T squared plus 48T plus 432. Those of you who have been through physics and looked at stuff like this, have you seen this projectile motion thing before? Do you remember what this number is here? That's in the plate instead of negative 16. What is this number? It's negative 4.9 usually, right?
oh yeah.
So how is this number related to gravity? It's half of that, right? How is 4.9 related to 9.8? So I mean, it all works the same way. It all comes back to, you know, you're starting with a constant gravity and then the antiderivatives from there. Just a matter of what units we're speaking. Any questions about how we got this function? Okay, so let's use it for some stuff. So let's remind ourselves of what this thing is. H of T equals negative 16T squared plus 48T plus 432. All right, and I want to know, when is the ball going to reach the highest height, its maximum height? How did you know that?
It forms parabola, so when the direction changes, that's the easier.
Okay, so you know how parabolas work,
And
and
I was going to say it's asking for a maximum, which means we know it has to.
so both of those are perfect. Yeah, perfect sets of reasoning to use. But yeah, and specifically to a parabola, if you can find out where the direction changes, which how would you do that again?
Finding the derivative and setting it equal to 0.
Yeah.
Positive.
Right. So, but either one of those things kind of depends on the idea of a derivative, right? What is the derivative of H of T? How'd you just do that?
We just did.
Okay, so I was curious if you took a derivative or you just read it, what we had before. So it should be negative 32T plus 48. Am I setting this equal to something?
Yeah.
0. That means T is equal to what? 3/2. All right. Did I answer the question yet?
No conscious patterns. That's just better.
What's the question?
Question, what is it reaches?
Yeah, I think I'm happy with that.
So at that amount of set.
Yeah. So that's when it happens. Any questions there? All right, now I want to know when it hits the ground. When would that happen?
When h of t equals 32.
You're on the right track. I think it's the way that I intended this, and maybe it's just not totally clear. I want h of t to be 0. Because basically I'm already starting above the ground. So the thing that I called h equals 0 was the ground, not where I threw it from.
Okay.
And that's probably more on me than it is on you. So yeah, the key here is I want to know what time makes h of t equal to 0. So negative 16t squared plus 48t plus 432 equals 0. All right, how do I solve this thing? I think I cooked this up so that all those numbers are divisible by 16. So it should be t squared minus 3t okay. I don't think that factors. Don't think. No. So quadratic formula it is. So t equals 3 plus or minus the square root of 9 minus 4 So how many times should I get out of this? Should get 2, right? So let's get them. So I have 6.9 seconds. And negative 3.9 seconds. How do I feel about those numbers? How come the second one doesn't matter?
You can have negative seconds.
Right, so I mean that's this, yeah. I only started measuring something that makes sense for this function from time, yeah, from not for non-negative values of time. So t equals 0 and greater. How we doing? Okay. That's all for chapter 4. All right, so basically we got, I was about to say one chapter left, but really we're not going to do all of it. Chapter 5 is the last one we're on. We'll do the first 4 sections and then you will pick up in Calc 2, right, where we leave off. So the last section we just looked at was, talking about these things called antiderivatives. This feeds, and you'll see very soon, this leads into this section, this chapter, which is all about these things called integrals. So you'll see how these are related to derivatives, but for now, just know that they are, and you'll definitely see some similarities, some connections. Looking ahead to the next test, which did I give you a date for that? I feel like I did.
2 weeks from.
Yeah, so 2 weeks from Monday. It'll all of chapter 4 and then 5.1 and 5.2.
This next go 21 or 5.
All right. So basically integrals mean, let's just think back to derivatives. What's the point of a derivative? Like, what does it actually tell you?
Instantaneous rate of change.
Instantaneous rate of change of what? What kind of thing? a function, right? So still dealing with functions. Now we're doing a different thing. So probably the quintessential like math textbook classroom example is I have a graph of a function, you can find the area underneath it. So this is the kind of one of the first things we'll do with integrals, but also, you know, we kind of saw an example of this just now. You know the speed of an object at any time. Can you find the position at any time? Which hopefully you can answer that question. Yes, you could do that. We just did something a lot like that. We think we have an idea about how something grows or decays with respect to time. Can we find out how much substance there is over time? And just to kind of give some perspective on how this is used, one of the first classes I took when I came back to ASU was a class called Mathematics and Cancer. And a lot of the things we did was basically modeling how tumors grow over time and how they get killed by treatments over time. And all those things are basically you're modeling integrals. And a lot of that research is saving lives right now. So yeah, a lot of these things are very, very important. They're not just classroom stuff. This one's just a classroom thing though. I want to find the area under this curve. We got to crawl before you walk. So I want to find the area under this thing. This is not a circle or a triangle or something we have a formula for. So really, we're going to take a guess at it. So how could I make an estimate for how to find the area underneath this curve?
Different shapes.
Okay, I want to split it up into different shapes. Any specifics?
You can make a horizontal line on the table.
A horizontal line at this minimum?
Yeah.
Okay. Like all the way across?
Yeah.
Okay. You've seen me make horizontal lines. That one's perfect, right? Horizontal line. So what do you want to do with that horizontal line now that we have it?
Oh, you can get the area of the rectangle under it.
Okay. And usually they're closer than that. Let's try. So we got the area underneath that, right? How good of a guess is that going to be for this area here?
Not good, but you can do one on top too.
Okay. So what else? So yeah, we're decomposing it into shapes that we understand how to find areas of, right? So what else could we do?
You could do a vertical line, like on the maximum, and then you can make a square out of that.
Make a square how?
Well, yeah, if you make a horizontal line, kind of that vertex on the right side.
Okay, so where the shading ends?
Yeah.
A horizontal line, you said?
Yeah.
Okay, so now I got a couple of rectangles I can find areas of. So is that a better guess? If I find those two areas?
Yeah, we can still keep going.
Okay, Isabel, what do you got?
I just have like a question, but could we use the critical points and then also like a point of inflection? Because it changes like concave, like you do those sections.
Okay, so yeah, I see an inflection point about.
And now I guess solve the issue in the middle, so you can do that to the critical point and that to the other.
Okay, so that right there, I can use a triangle, right? Nothing says I have to use rectangles. So I can use that triangle. And I'm gonna have some, I'm gonna have this white space in here that is gonna end up being an overestimate, right? But I'm also gonna have some of this purple space that I'm not gonna count. So maybe that'll balance out a little bit. So I can keep doing this over and over, right? And keep breaking it down into smaller shapes, but I'm never going to get to the right number, right? But that's a good place to start. So let's do something really, really simple. We're just going to use rectangles. And not only are we just going to use rectangles, we're just going to use them. They're all going to be the same width. They're all going to be vertical, and they're all going to have the same height as this function. And specifically, whatever the right-hand height is. So this interval goes from 0 to 1, right? So how wide are all of our rectangles going to be? And I'll call that measurement delta x. If I want to make 4 rectangles, how wide is each one going to be? 1/4. Because the interval is 1 unit long. It's going to get divided into 4 equal pieces. So I have these rectangles are 1/4 in width, right? So I can basically divide up or partition up my X interval into these 4 chunks. And now I'm going to draw rectangles. So how good of an estimate is this thing going to be? Let me ask it this way. Am I going to be wrong?
Yes.
Which way am I going to be wrong? It's going to be an overestimate, right? So now that we've admitted that to ourselves, let's go ahead and get the estimate anyway. So how would I find, so I basically have taken this parabola, I've split it up into 4 rectangles, even though it's not a faithful approximation. It's a good place to start. How would I find the areas of these 4 individual rectangles? Let's start from the left and go right. How would I find the area of that first rectangle? Length times width. So in general, we're using rectangles. So yeah, area equals length times width. So let's do that specifically for this function we care about here. What's the length? You know what? Instead of calling it length by width, I'm going to call it width and height to make it more clear what we're looking at.
So then it's 1/4 times 1.
From the left.
Sorry,
So let's start from the left. So I agree with you that it's going to be 1/4 times something, right? What is that? What's the height really? More importantly, how do I find the height? Right. So it's going to be 1/4 times. Let me write this in the reverse order. It's going to be f of 1/4 times 1/4, right? Okay. We'll plug in later, but how would I find the area of the second rectangle? What's the width? The width is still 1/4, right? So am I still saying f of 1/4 for the height? So for now, I'll call it f of 2/4 just to make it clear what we're doing. So we're sampling at these like regular 1/4 intervals, right? So first rectangle, I'm pulling my height from the right end of these rectangles. So this is f of 1/4, f of 2/4, and then how would I find the area of that next rectangle? No, I'm still on the third. I'm on the third rectangle. 3/4, right?
What is that f of like the 1/4, 2/4? What is that symbolize?
F as in the function. So I'm calling f of x equals x squared.
Okay.
So f of 4/4 times 1/4, right?
Okay.
So basically, to find the area underneath this curve, I'm going to instead treat these little subsections of this function as rectangles and find those areas, as many as I want, and add them all up, right? So can I get a number here? What is f of 1/4? 1/16? F of 2/4 will be, just keep them all in these unreduced forms so I can have a common denominator. So plus 9/16 times 1/4 plus, I'll just keep that one, 1/4.
Are we assuming each rectangle doubles in height?
No, it doesn't, does it? So let's be clear, where are we getting the heights of the rectangles?
From the function.
From the function, right? So this is a very simple y equals x squared, but we could do this for any kind of function, right? So let me end by getting a number for this. So 1/64 plus 4 plus 9. (30/64). I'm pretty sure that's good. 1/64 plus 4/64 plus 9/64 plus 16/64. Yeah, okay. All right, so we got an area of 1536, so we think that's close.
It's likely gonna be over.
Likely to be over, or absolutely, it certainly is, right? So what we're gonna do next time is get better estimates and see if we can get this exactly, but yeah, this is our first little touch on integration. All right, I'll see you all